Welcome back to the deep dive. This is where we take source material, the research papers, articles, maybe even your notes, and we really dig in.
Yeah, we're not just scratching the surface. We aim to pull out those key insights, the things that really make you think.
Exactly. Helping you understand what actually matters. Think of it as your way to stay ahead, plugged into the really cutting-edge stuff. So today, we've got a paper that landed in May 2025. It's titled Parallel Scaling Law for Language Models.
Ah, yes, this one's from researchers over at Zhejiang University and also the Quinn team at Alibaba Group.
Right. And if you're working in AI, maybe machine learning, perhaps training models, deploying them, well, this one's definitely for you.
It really is relevant.
So our mission for this deep dive, we want to get our heads around this new way they found to scale language model.
Whole new paradigm, really.
Yeah. What does it mean for building better, more efficient AI? And why could it actually change how we think about getting these models out there, especially onto hardware that's, well, less powerful?
Like phones or embedded systems. Big implications there.
Okay, and for everyone needing the quick version, the real short-form takeaway, researchers have found a third major way to scale up language models.
Beyond just adding parameters or giving models more thinking time at inference.
Exactly. They call it parallel scaling, or PARSCALE. And the clever bit is you scale computation both during training and inference by running several parallel streams. But, and this is key, using the same core model parameters.
Right, the same base weights.
And their new scaling law. It shows that adding, say, p parallel streams can boost capability, kind of like adding parameters, but by a factor related to the logarithm of p think O log p.
Which is interesting in itself, that logarithmic relationship.
But the really big win, especially for deployment, inference efficiency. PARSCALE gives you similar performance boosts, but with way, way less extra memory needed. They measured up to 22 times less increase.
Wow.
And less extra latency too, up to 6 times less increase compared to just making the model bigger.
So that makes it potentially huge for putting powerful AI on devices with limited memory, right? Phones, robots, that kind of thing.
Exactly, a potential game changer for the edge. Okay, let's dive deeper then. What was the actual problem they were trying to crack here? Why invent another scaling method?
That's a great starting point because, honestly, the existing methods have some pretty serious drawbacks, especially as models get bigger and bigger.
Which they always seem to be doing.
Right.
Yeah.
So the paper lays out the landscape. You've got your traditional parameter scaling. That's the most common approach.
Just make it bigger, add parameters, mixture of experts maybe.
Precisely. And look, it works. We've seen amazing results. But the space cost, the memory footprint, it's just enormous.
Yeah.
Think about models hitting hundreds of billions of parameters. The paper mentions DeepSeek v3 at 672 billion. Trying to deploy that, you need massive infrastructure.
Forget putting that on your phone.
Absolutely not. Edge deployment is basically off the table for those monsters.
Okay, so that's one scaling route. What's the other main one?
The other is inference time scaling. This is where you give the model more compute time when it's generating an answer.
Like prompting it to think step by step, generating those reasoning tokens.
Exactly, generating intermediate steps, kind of like showing its work. It can be really effective for complex problems, boosting reasoning, but it has a lot of time. Latency goes way up.
Right.
The paper gives an example where, even for a simple math problem, a model might spit out hundreds of these extra reasoning tokens. That takes time. Plus, it's often task-specific, needs special data or careful prompting.
So it sounds like you're often choosing between a model that's too big to fit anywhere useful or one that's smart but too slow for interactive use. Kind of stuck.
Pretty much. Too much space cost or too much time cost. And that's the gap they aim to bridge. They wanted something more universal, something that scales capability efficiently without these massive memory or latency penalties.
Especially thinking about deployment beyond just giant data centers.
Exactly. And their inspiration, interestingly, came from a different domain diffusion models for image generation.
Oh, how so?
Well, there's this technique called classifier-free guidance, CFG. Often, it involves running the diffusion model twice, once with guidance, once without, and mixing the results. And somehow, this simple trick of just running it twice makes the pictures better. The authors here looked at that and thought, wait, maybe the benefit isn't some magic property of guidance itself, but simply the fact that you're using twice the computation.
Ah, okay. More compute equals better results, potentially.
Yeah, that was their hypothesis. Could scaling the amount of parallel computation while keeping the actual model parameters mostly the same give you capability gains similar to just adding more parameters?
That's a neat conceptual leap. And the mechanism they proposed, PARSCALE, seems to follow directly from that. How do they describe implementing it?
It's conceptually quite elegant, like you see in their figure 1. You take an input, you apply p different simple transformations to it, create p slightly varied versions.
Okay.
Then you run these p inputs through p parallel copies of the same core model.
Okay.
So p forward pass is happening at once.
Using the same weights, though.
Critically, yes. Same base model weights. Then you take the key outputs from these parallel runs and you dynamically combine them, maybe using a weighted average, to get your final single output.
And how did they actually do those transformations in the combining part?
For making the inputs different, they tried a few things, but settled on prefix tuning. Basically, you add small, learnable vectors prefixes to the input embeddings for each of the p streams.
So each stream gets a slightly different nudge.
Kind of, yeah.
Huh.
It effectively gives each stream a different starting point or context via the KV cache. And interestingly, they found that just randomly initializing these prefixes often work well enough to create the needed diversity between the streams.
Huh. Okay. So it doesn't need to be super complex.
Apparently not for the input side. And for combining the outputs, they used a small MLP, a tiny neural network, to learn the best way to dynamically weight and average the p outputs.
Adding minimal extra parameters, I assume.
Very minimal. They mentioned something like 0.2% extra parameters per stream. The really crucial finding, though, was that the performance gains seemed driven primarily by p, the number of parallel computations, rather than the specific details of the prefix tuning or the aggregation method.
Got it. So p is the magic number here. Okay, they have the idea, the mechanism. But does it scale predictably? Like, is there a law for this similar to how we have scaling laws for parameters?
That's exactly what they propose next. A new generalized scaling law that incorporates this parallel computation factor. Yeah. This is maybe their main theoretical contribution.
Okay, how does that work?
They looked at it theoretically, sort of like viewing PARSCALE as an ensemble prediction method where the ensemble members share almost all the parameters.
Right, like multiple experts, but they all read the same textbook.
Kind of, yeah. And in ensemble theory, performance gains come not just from how good each member is, but also how different or diverse they are. Their theory connects the loss reduction to this diversity factor between the p streams.
Makes sense. If all streams do exactly the same thing, adding more won't help much.
Precisely. Their theoretical formula suggests that the loss should decrease roughly inversely with p as long as the streams aren't perfectly correlated. They even speculate that maybe CFG works so well because the conditioned and unconditioned passes are somehow negatively correlated, increasing diversity.
Interesting angle on CFG, but okay, that's the theory. Did the experiments back it up?
They did quite extensive experiments, large-scale pre-training, the kind you do for foundational models. They used two main data sets.
Which ones?
Stack v2, which is mostly Python code.
Okay. Requires logic reasoning.
Right. And the Pile data set, which is a big mix of general text, more about broad knowledge, maybe memorization.
Got it. And they varied the model size and the number of parallel streams.
Yeah. Model parameters, n, from around 500 million up to 4.4 billion. And the parallel streams, p, from 1, which is just your standard single model, up to 8.
And what did the results show? Did the law hold up?
It really did, quite impressively. They fitted an empirical scaling law to the results. It's a bit mathematical, but the key takeaway is it shows the loss improves with both n parameters and with the logarithm of p, parallel streams.
The O log p relationship again?
Exactly. The formula looks something like loss is proportional to 1 divided by n times k log p plus 1. And the fit was remarkably good, R-squared values, up to 0.998.
Wow, that's a tight fit. So the data really supports this logarithmic scaling with parallel computation.
It strongly suggests it, yes. It's not just a random effect. There seems to be a predictable scaling relationship here.
And that k value in the formula, what did that tell them?
K is interesting. It basically represents how much benefit you get from adding parallel computation. And they found K was noticeably higher for the Stack v2 coding dataset, around 0.39, compared to the general Pile dataset, around 0.33.
Okay, wait, so parallel computation helps more on the coding tasks than on the general knowledge tasks.
That's what the data suggests, which feeds back into their intuition.
That parameters are maybe more about memorization, General knowledge absorption strong on pile, while computation, especially this parallel kind, helps more with reasoning, logic stronger on stack v2.
Exactly their conjecture. Parameters build the knowledge base, computation enhances the processing of that knowledge, especially for reasoning-heavy tasks.
And you can see this visually in their plots too.
Yeah, figure 3 is quite revealing. It shows loss contours based on n and p. You see both help reduce loss, but as the model gets bigger, n increases, the lines flatten out horizontally. Adding more parameters gives diminishing returns compared to adding more parallel computation, increasing p.
So for large enough models, boosting computation via PARSCALE might be a more efficient path to better reasoning performance than just adding yet more parameters.
That seems to be the implication, particularly for certain capabilities.
Did this translate to downstream task performance as well?
It did. They tested on various benchmarks. Increasing P generally helped everywhere, but the gains were consistently bigger on coding and math problems compared to, say, common sense reasoning or question answering based on the pile training.
Can you give an example?
Sure. They showed their 1.6 billion parameter model run with P8 could match the coding performance of a much larger standard 4.4 billion parameter model.
Wow.
But on the general tasks trained on pile, that same 1.6B P8 model performed more like a standard 2.8 billion parameter model. Still better, but not as dramatic a jump as for coding.
Okay, so parameters still clearly matter for breadth, but PARSCALE gives a significant boost, especially on the reasoning side.
Precisely. It confirms that computation isn't just a substitute for parameters. It seems to enhance certain aspects more than others.
All right, the science seems solid. PARSCALE works, it scales predictably like O log P, boosts reasoning. But now the crucial part for anyone deploying models, efficiency. Does P parallel streams mean P times the inference cost?
This is really where PARSCALE makes its strongest case for practical use. And the paper makes a good point. When we talk inference cost, raw FLPS isn't always the main bottleneck. Especially for generating text token by token, memory bandwidth, particularly for the KV cache, is often the real constraint.
Right, constantly accessing that cache.
Exactly. So they focused on memory, space cost, and latency, time cost. And for memory, the results are pretty striking.
How so?
PARSCALE adds very little extra memory overhead. Remember, you're using the same big block of model parameters p times. The only new memory is for those small prefixes, the tiny aggregation network, and yes, P copies of the KV cache.
Okay, the KV cache scales with P.
It does, and with batch size. But compared to adding billions more parameters like in traditional scaling to get similar performance, the PARSCALE memory increase is often negligible.
Much smaller increase. Makes sense. What about latency, the time it takes? Running P passes sounds slower.
You'd think so, but especially at small batch sizes, which is typical for edge devices, maybe batch size 1, the latency increase was surprisingly small.
Why is that?
Modern GPUs are just really good at parallel processing. Running those P-forward passes simultaneously doesn't necessarily become the main bottleneck if the batch size is small. They found PARSCALE was actually faster, lower latency increase for similar performance, than parameter scaling up to a batch size of 8 in their setup.
Okay, so give us those headline numbers again, the practical comparison.
Right. The standout example was take a 1.6 billion parameter model. To reach a certain performance level, using PARSCALE with PIC8 required up to 22 times less additional memory.
22 times.
And up to 6 times less additional latency compared to achieving similar performance by just scaling up the parameters of a traditional model.
That's a massive efficiency gain, especially on the memory side.
Huge. It directly addresses the memory wall that often prevents deploying larger, more capable models on resource-constrained devices.
Okay, inference efficiency looks like a major win. But let's talk training. That's the elephant in the room, right? Training P streams must mean P times the compute cost during training.
It does fundamentally increase the required training computation by a factor of P. Yes, you were doing P forward and backward passes. That's the trade-off. But they proposed a way around doing that for the entire training process.
Ah, a practical strategy. What is it?
Two-stage training approach.
Okay, stage 1.
Stage 1 is just standard pre-training. You train your base model like usual on the vast majority of your data. Let's say 1 trillion tokens, like in their big experiments. Normal P1 training.
And stage 2?
In stage 2, you introduce the PARSCALE components, the prefixes, the aggregation network, and you continue training, but with P parallel streams. Crucially, though, you only do this stage 2 training on a much smaller data set.
How much smaller?
In their example, they used only about 20 billion tokens for stage 2. That's just 2% of the stage 1 data.
Only 2%. And does that short second stage actually work? Does the model learn to use the parallel streams effectively?
That's what they showed in Figure 5. It works remarkably well. When you switch to PARSCALE in stage 2, there might be a tiny initial dip in performance as the new parts initialize, but the model adapts very quickly.
Okay.
And then it starts showing those same logarithmic performance gains with increasing P, just like if you'd trained with PARSCALE from the very beginning.
So you don't need P times the compute for the whole training run, just for a small finishing stage.
Exactly. It makes the overall training cost much more manageable, much closer to standard training.
And they validated this two-stage approach on downstream tasks, too.
Yes. Table 4 shows results after 1 trillion tokens of stage 1 training, followed by the short stage 2. The pattern holds. Consistent gains from increasing P, especially again on math and coding tasks, the strategy delivers.
That's pretty convincing. And they didn't stop there. They even tried applying PARSCALE to a model that was already fully trained, right? An off-the-shelf one.
Yeah, they took the Qwen 2.53b model, which had already been pre-trained on a massive 18 trillion tokens, a state-of-the-art model.
And could they add PARSCALE capability to it after the fact?
They showed 2 things. First, just continuing pre-training using their 2-stage PARSCALE approach still improved performance, so you can enhance existing models.
Okay.
But even more interesting, perhaps, was the parameter-efficient fine-tuning, or PFT result.
PFT, so freezing the main model.
Exactly. They froze the entire multi-billion parameter Qwen backbone. They only trained the tiny number of new parameters introduced by PARSCALE, those input prefixes, and the output aggregation weights.
And that worked, just training those few extra weights.
It worked effectively. It allowed the model to leverage the parallel streams and gain performance without touching the original weights.
Now, that has some really powerful implications for deployment, doesn't it?
Absolutely. It leads directly to their idea of dynamic parallel scaling. Meaning you could deploy a single base model, say that Qwen model.
Yeah.
Then during inference, depending on the task difficulty or the available memory or how fast you need the answer.
You could just choose how many parallel streams to run.
Precisely. You could switch between P1 for simple fast queries, maybe P4 for medium tasks, or P8 for complex reasoning when you have the resources, all using the same core weights.
Wow, okay, so you get scalable performance levels from one deployed artifact just by adjusting the computation on the fly. No need to load different models.
Exactly. It offers a whole new level of runtime flexibility and resource management. Choose your compute performance trade-off dynamically.
That feels really practical. So stepping back, how does this PARSCALE idea fit into the wider research landscape? They mention connections to CFG ensembles.
Yeah, they position it thoughtfully. They see it as generalizing existing scaling concepts by explicitly adding computation as a scalable dimension alongside parameters. And it provides a more formal, principled explanation for why techniques like CFG might work, linking it back to computation and diversity.
So it's not just a random trick, it's potentially part of a broader scaling picture.
That's the argument. It builds on ensemble ideas, but with massive parameter sharing, and it offers a universal approach, unlike some task-specific inference time methods.
And zooming way out, this really digs into that fundamental question. What actually makes a model capable? Is it just the number of knobs, the parameters, or is how you turn those knobs, the computation, just as important?
Right. And this paper, with PARSCALE and the ON log P law, offers a new lens, a quantitative way to think about that ratio. It suggests parameters give you the raw knowledge and representation.
The what?
And computation, especially parallel computation like this, enhances the how effectively the model processes or reasons using that knowledge. PARSCALE seems to be a particularly efficient way to boost the how for certain tasks.
A way to balance N and P for optimal results.
Potentially, yeah. Finding that sweet spot. So wrapping up the main contributions here, PARSCALE is introduced as this novel scaling strategy. It's efficient, especially for inference memory and latency.
Backed by that new ON log P scaling law.
Right, with major benefits for edge deployment. Plus, they show practical ways to train it using the two-stage method and even adapt existing models using PFT.
Which enables that cool dynamic scaling idea.
Exactly. A lot of significant contributions packed into one paper.
Definitely feels like a new tool, maybe even a new dimension to consider when building and deploying these models, particularly as AI keeps moving closer to the user onto devices. So, okay, here's something for you, our listeners, to chew on after this deep dive. If PARSCALE really lets us trade computation for parameter count, especially to boost reasoning in smaller models, how might that fundamentally change how we design and deploy AI in the future?
Yeah, think about the economics, the hardware requirements.
Will we see a trend towards models specifically designed to leverage this computational scaling on edge devices, prioritizing this P factor over just piling on more N, more parameters? What new applications become possible when capable reasoning can happen locally, faster, and maybe more privately?
Lots to consider there about the future architecture of AI systems.
Definitely something to think about. That's all for this deep dive. Thanks for tuning in.
We'll catch you on the next one.